Welcome to the deep dive. Today we're heading way, way back, almost to the beginning of everything.
That's right. We're looking at the universe's baby pictures, in a sense.
Exactly. Not with telescopes looking for galaxies, but by searching for this tiny, subtle twist in the oldest light there is. Our topic is cosmic birefringence, probing parity violation in the universe.
It sounds complex, but the core idea is fascinating.
It really is. So our mission today is to unpack what cosmic birefringence actually is, why scientists think it might point to, well, new physics, and how they're trying to measure it using the cosmic microwave background.
That faint afterglow of the Big Bang.
Precisely. And joining me is our expert, who's fantastic at making these huge cosmic ideas clear.
Happy to be here.
Okay, let's unpack this then. For those of us, who aren't cosmologists day to day, what exactly is cosmic birefringence?
Okay, so think about light having an orientation, a direction. We call it polarization.
Like sunglasses cutting glare.
Exactly like that. Now, the cosmic microwave background, the CMB, this ancient light, it has polarization patterns. We sort them into two main types.
All right.
There are E modes, think sort of simpler radial or tangential patterns, and then there are B modes, which are curlier swirling patterns. B modes are often linked to things like gravitational waves from inflation.
Right, the really early universe stuff.
Yes. Now, cosmic birefringence is this idea, this effect, where the universe itself could twist the E mode patterns slightly, turning them into B mode patterns as the light travels towards us.
Wait, the universe itself twists the light.
That's the hypothesis. It's a rotation of the polarization plane.
Okay, that sounds subtle. But why is finding this twist such a big deal? What's the deeper meaning?
Well, that's the crucial part. Finding this rotation wouldn't just be, an interesting astronomical observation. It would strongly suggest a fundamental asymmetry in the laws of physics.
Asymmetry. How so?
It's thought to be caused by something called parity violating processes. Basically, parity violation means the laws of physics might not be identical if you viewed them in a mirror.
Like they have a handedness. Left isn't the same as right at some deep level.
Exactly, a fundamental handedness. If we confirm this cosmic birefringence, it suggests the universe, at its core, might prefer one direction over the other. This could hint at physics beyond our current standard model, maybe even explain some big cosmic mysteries.
Wow. A handedness to the entire universe.
Yeah.
There's a lot to think about. It connects to our very existence, maybe.
Potentially, yes. It challenges fundamental assumptions.
But, okay, measuring something that subtle across literally billions of light years, that must be incredibly hard. What makes it so challenging?
Oh, it's extremely challenging. You're right. One of the biggest problems is something we call degeneracy.
Degeneracy.
Yeah, it means it's hard to tell one effect from another. In this case, the faint cosmic rotation signal looks almost identical to a rotation caused by a tiny miscalibration in our telescope detector's polarization angles.
Ah, so your instrument could be fooling you, making you think you see a cosmic twist when it's just the telescope itself.
Precisely. How do you separate a real signal from the dawn of time from a tiny instrumental quirk happening right now? That's the core difficulty.
That sounds like a nightmare. Finding that cosmic whisper in an instrumental hurricane, like you said. So how do researchers tackle that? Is there a clever trick?
There is, thankfully. The main proposed solution involves using emission from our own Milky Way galaxy, galactic foreground emission.
Using our own galaxy's light. How does that help? Isn't that just more noise?
It seems counterintuitive, I know, but we can map the polarization of our galaxy's light pretty well. Since this foreground light passes through the same telescope optics but doesn't have the cosmic birefringence effect, we can use it as a calibrator.
Like a reference point.
Exactly. By comparing how the telescope sees the known galactic polarization versus the CMB polarization, we can sort of self-calibrate and figure out how much rotation, if any, is being added by the instrument itself.
Okay, that is clever. Using the foreground problem to solve the calibration problem. Has this technique actually worked in practice or maybe in simulations?
It's shown a lot of promise, especially in detailed simulations. People have simulated data like what the Planck satellite's high-frequency instrument saw.
Planck, right, the big CMB mission.
Yes, and these simulations showed the method is quite robust. It holds up well against various instrumental issues like intensity leaking into polarization signals or beam imperfections, things like that. It seems pretty good at isolating the instrument's contribution.
That sounds really promising. So, are we there yet? Or are there still hurdles?
We're closer, but there's still a significant hurdle. Even with good instrument calibration, the method is still sensitive to something called the EB correlation of the polarized foregrounds themselves.
Okay, what does that mean?
It means the dust and gas in our galaxy, the stuff emitting that foreground light, might naturally have patterns where its E modes and B modes are correlated in a way that also mimics the cosmic birefringence signal.
Ah, so the galaxy itself could be creating a false positive, even if the instrument is perfectly calibrated.
That's the remaining challenge. It's like trying to hear that faint cosmic tune when the galaxy itself is playing a very similar tune right on top of it.
Right. So how do we get past that for a definitive measurement? What's the next step?
The path forward involves much more sophisticated modeling. We need to correct for this foreground bias using detailed templates of the galactic emission, likely derived from complex statistical methods like Bayesian component separation.
Sounds data intensive.
It is. It absolutely requires next-generation, high-precision CMB polarization data. And crucially, we need a much better understanding of cosmic dust polarization going beyond the simpler models we often use now.
So better data, better models of the messy stuff in our own galaxy.
That's the plan for getting a clean, definitive measurement.
This whole area is just incredible. These tiny, subtle twists in light that's traveled for over 13 billion years.
Yeah.
They might hold the key to whether the universe has this fundamental asymmetry, this hidden handedness.
Yeah. It's a frontier of fundamental physics, probed by looking at the biggest scales.
It really shows how scientists are pushing right to the edge, doesn't it?
Yeah.
Trying to wring out secrets from the universe's oldest light. So what does this mean for you, listening? It means the cosmos might still hold profound secrets about its own fundamental rules. And this hunt for cosmic birefringence, it's bringing us closer than ever to potentially uncovering them.
A potential revolution in our understanding, hidden in plain sight.
Thank you so much for joining us on this deep dive.
My pleasure.